Thanks, Jeff. I just I'm getting over a cold too, so you'll have to pardon my hoarse voice. Jeff already introduced me. That's the name of my project. All right, so this is just a quick outline of the order of topics I'm going to discuss. This is not a typo. There's actually two hypotheses involved in my study, and I'll explain that when I get to that part. And this tree actually is probably what most people know the White INYO Mountains for, which is the bristlecone pine forest. And this is allegedly Methuselah, which is supposed to be the oldest single tree from a single stem in the world, like 5,000 years old. So, where are the White INYO Mountains? Well, for those who don't know, the White INYO Mountains are on the California-Nevada border, and they border the eastern Owens Valley, and on the west lie Fish Lake Valley, Eureka Valley, and Saline Valley. And this whole area is controlled, most of these valleys are controlled tectonically. The range itself is north, south, and relatively contiguous. And it's separated by the unofficial boundary of Deep Springs Valley, and Westgard Pass, which is Highway 168, runs through the Deep Springs Valley and separates the two mountain fronts. So there are two problems that I'm addressing, and the first is there are significant discrepancies in the tectonic geomorphology along the White Mountains. It was observed by Phillips and Majkowski and others that had done a study. They noticed that certain aspects of the geomorphology implied greater uplift in the north, and certain geomorphic indices seem to contradict that. And then the second problem is there a more efficient way of measuring geomorphic indices? So I like this quote here from Anderson and DiPolo, essentially saying that techniques Bull and McFadden used are more laborious than desired for application. So in other words, pen and paper and pencil and paper take a long time to do. And so we want to know, is there a quicker way to measure indices? So the two hypotheses I came up with were the first, if the qualitative observations of Bull and McFadden, Phillips and Majkowski are true, then a quantitative analysis of the tectonic geomorphology along the White INYO Piedmont using multiple geomorphic indices may clarify controls on geomorphology. So if I do a robust geomorphic analysis, will I be able to find out why I see these discrepancies in the geomorphology? Second, if Google Earth is a suitable tool for calculating and measuring geomorphic indices, then replicating the geomorphic indices measured by Bull, McFadden, and Knott, 1998, using Google Earth should produce similar results. If this hypothesis is true, and then I can go back and test the first hypothesis. So the geology of the INYO White Mountains is complex. This is really just the White Mountains, though if you held a map of the INYO Mountains up, it would look similar, at least in respect to the spattering of color. So there's three zones, or three divisions I clumped the rock groups into. The first is Proterozoic to Permian. During this time period, metamorphosed sedimentary marine rocks are associated. Then during the Mesozoic, a series of granitic plutons, which are shown in this magenta color, are featured throughout the range, and a series of volcanics in the northern portion. And then from the Tertiary to Quaternary, there's a series of volcanic eruptions, lacustrine deposits, and then alluvial gravels, especially along the Basin and Piedmont intersection. So structurally, as I said, many of these valleys are controlled by faults. This is a figure I modified from Stevens et al. 2013, where they divided up the valley partly based on the fault systems, partly based on the geology, into a number of structural blocks, zones, and basins. And of primary concern to us, or to me rather, is the White Mountains block, the INYO Mountains block, the White Mountains structural zone, and the southern INYO structural zone, as well as the greater Owens Valley basin, which is subdivided up into these smaller basins. These blue blocks represent more coherent structural blocks that tend to move as a cohesive unit. And the pink zones here are much more heavily faulted and are not as coherent as the blue blocks tend to be. And then quickly as well, normal faulting is featured along the west side of the INYO Mountains, or White Mountains rather, and then a shift in basin polarity occurs, and the main mode of, or the main type of slip is strike slip along the West INYO Mountains. So previous work that was done in this area. Well, in regards to just straight tectonic geomorphology, Bull and McFadden are kind of the study that everybody you start out with. They started it all in a sense. In 1977, they developed geomorphic indices in extended terrain, and they happened to be just south of where I did my study area, which was beneficial. Wells et al. In Costa Rica applied indices to compressional terrain, so they expounded upon Bull and McFadden's work, and then Menges, that's right, in 1981 developed long-term indices. So how can we see if these geomorphic indices are expressed over long-term time spans? Leader and Jackson in 1993 looked at in the basin and range, basin fault fan relations in extended terrain, and then Knott in 1998. Dissertation or PhD dissertation was done in Death Valley, which is close to where I was at, and also did applied geomorphic indices from some of these studies as well in extended terrain. Along the White Mountains, geomorphological studies have been done by DiPaolo in 1989, who divided up the White Mountains fault zone into a number of sections based on fault scarps and fault scarp morphology. And Lease in 1991 did a study and she concluded that lithology was largely dependent on, that the primary control on fluvial morphology was lithology rather than tectonic or climate. And Whipple and Trailer in 1996 did a similar study measuring fans and basins, and they said no, lithology is not the most important. Tectonics is actually the primary control on lithology. They both agreed that in an arid environment, climate is minimal. Phillips and Mijkowski in 2011 did a study concentrating on fault, what controlled geomorphology, and they suspected that it was the angle of the faults. And this was done along the White Mountains fault zone. So the geomorphology of the area, going back to the previous figure, you can see that DiPaolo and Bryant subsequently divided the White Mountains fault zone up into a number of sections. DiPaolo originally divided up into 5 sections, which were the Montgomery, the Hamel, the Central, and the Wacoba, and then the INYO. However, DiPaolo himself said that this division between the Wacoba and INYO was rather arbitrary, and in 2000 Bryant combined the two sections, and based on results of my study, I concluded that Bryant's analysis was correct, or at least I agree with it more, in that these should be clumped together, the Wacoba and INYO sections, and so that's what I adopted for this study. So the various methods that I used. Geomorphic indices that I applied are listed here. And for instance, the mountain front sinuosity, this is the mathematical derivation, and it works by dividing the length of the mountain front sinuous path, which would be this, and divide by the straight line, which would be this. And then these are the Google Earth tools that I used to calculate that using Google Earth. So the higher the ratio, the lower the tectonic activity associated with that ratio. The lower the ratio, I said it right, the lower the ratio, the higher the tectonic activity is associated with it. This is valley floor width to height ratio. In this case, more V-shaped valleys are associated, and higher ridge lines are associated with a more tectonically active area, and then a U-shaped valley is associated with less tectonic activity. Basin elongation, more elongate valleys are found in areas of higher tectonic activity. When tectonic activity decreases, it is often associated with more round valleys. For basin area to alluvial fan ratios, we often find smaller alluvial fans, more narrow alluvial fans along areas where tectonic activity is higher. For basin relief ratios, we see higher relief along a basin in more tectonically active areas. And then for the stream concavity index, this is a normalized profile of the stream channel. And what tends to happen is that as uplift occurs quickly this becomes more concave or convex upward and approaches this normalized line right here. And a lower value implies less tectonic activity, so lower ratio, and a higher value implies greater tectonic activity. Two methods that I did not show on here but I used as well were range crest Piedmont intersection profile, and I will show an example of that later on in the results section, and that essentially is a comparison of the range crest to the Piedmont and how they interact with one another. And Megan's observed that oftentimes along areas where you have a significant change or a sharp drop or increase in elevation, it can be associated with a fault boundary or a section boundary. And then range front strike, which is the change of strike along a range at a certain segment. In this case, I used 1 kilometer or greater segments, which also can indicate a change in fault strike. So Google Earth. So I figured it probably would be useful to show everyone what I did in Google Earth. And so I'm going to briefly leave the PowerPoint and open up Google Earth right here. And this right here is a side view, so we're facing relatively east. And this is the White Mountains. So this would be the north, White Mountains. This is Queens Valley right here. And then this would be towards the south. So first thing I need to do is obviously identify my canyons that I was going to be measured. I measured a total of 57. So that was fairly easy with those buttons. I could drop those. And then I measured mountain front sinuosity. You can see the sinuous is represented by these red lines, and the straight lines are represented by these straighter yellow and purple lines. The only reason they're those colors is just so I could easily differentiate them from one another. Stream concavity profiles, I did them for not all of the streams, but a total of 17 of the streams. And you can see they go from the range crest down to the valley floor. Valley floor height ratios. Cross sections were measured. I'm going to zoom in real quick. Along these green lines here, and these blue lines represent 1 kilometer up from the intersection of the canyon mouth and the basin floor. So one of the interesting things and one of the helpful things with Google Earth are these elevation profiles that you can show yourself. So you can see here where I'm at located on the ridge, and I can see the elevation on both sides of the ridge, and I can see the elevation, and I can measure the distance of the valley floor. So zooming back out. There we go. Alluvial fans. I measured alluvial fans for all of the 57 drainages that I measured. Range crest profile. The purple line represents the crest. The sinuous already provided the Piedmont profile or trace for me. And then I used a line to segment out the distance between each point I measured, which was 500 meter intervals. And then this is a straight line here, making sure that I measured perfectly perpendicular to the range crest and the Piedmont. Basin areas. Yeah, basin areas, you can see where I outlined the different basin areas. And then basin relief, I had identified the highest point in the basin with the lowest point of the basin at the canyon mouth. And then range front strike, which is represented by these blue lines. So I did this for the entirety of the White Mountains, and then I also did it for the INYO as well. So you can see I got a lot of data. All right, I'll go back to the presentation now. So that's what I did in Google Earth. So what were my results? Well, let's start out with the replicated study. Studies are replicated, rather. So the first one I replicated was McFadden's study. And I did replicated the entirety of their study, both the mountain front sinuosity and the valley floor with the height ratios. This is the mountain front sinuosity trace on Google Earth. So this is what it looked like when I was done. And I found that I was able to replicate 90% of their study with either dead on or within less than a standard deviation of difference from their calculated values. So right here, you can see the mountain front and direction. So this is it correlates with those lines we saw before on the previous slide. This is the mountain front sinuosity that McFadden calculated. This is my reproduced mountain front sinuous, and this is my reproduced straight line measurements. and then this is my reproduced sinuous ratio. And you can see, compare mine to theirs in these two columns, and then this is the difference between the two. So as you can see, the majority of these were right on or within range of what they calculated. Quickly, the class, what this is referring to is for tectonic activity, at least with this mountain front sinuous, Bull and McFadden basically said that lower values are indicative of a higher tectonic class. So a 1 would be very active mountain front, and you can see that that roughly corresponds with a sinuosity value of 1. A 2 is slightly active, and then a 3 is inactive. And you can see that with all these except for this particular line, they're close. So the highlighted line here, the Argus range, what happened? Well, there's two explanations why I believe I have different values from them. And the first is that this is the very first sinuosity, the first study I replicated, and so I probably got better at drawing mountain front sinuosities as I did more of these. However, another key component, I think this is also a large factor, is that I believe Google Earth is much more precise than what they used. They were using topographic maps, whereas Google Earth I can pretty much tell within a meter of what the what my measurements are, and also my contour lines, or the equivalent of. All right, so this is Figueroa and Knott. This is, I needed to also look at Google or ArcGIS, and how does Google Earth compare to ArcGIS, because that's another method of measuring geomorphic indices. And so Figueroa back in 2010 did this profile of the Kern River, and I want to see if I can replicate that with similar results with Google Earth. I believe that I did. I think this shows this. You can see the nick points at the same point in the profile, and you can see that in general the gradient follows the same path, and then even here where the fault happens and this empties out into the Central Valley, you can see a similar profile. And there are a couple of blips that are different, but over a 220 kilometer distance, I think it demonstrates fairly effectively that Google Earth can be used. And then finally, Phillips and Michkowski. So I wanted to test the efficacy of Google Earth and the accuracy of it, looking at area ratio or areas of alluvial fans and basins, because basins in particular are used in a number of geomorphic indices. So I reproduced two of their results. You can see their 0.01 difference between their ratio for fan and alluvial fan and basin area ratios, and my replicated ratios. And then for Silver Canyon, it's the exact same. So I felt that these Google Earth could be trusted to safely measure areas. And I also want to point out that these are subjective measurements, if ever there was a subjective measurement in geomorphology when you come to alluvial fans. And to be able to get to this close to what they did, I thought was fairly impressive. So the results. Basin elongation. The results of my study, rather. Basin elongation. This is a graph of the basin elongation ratios. This is a latitudinal profile, so this would be the north section. This would be North White Mountains, and this would be the south section. So this would be the south of the INYOs. These are typical results that we find through most of the geomorphic indices. Higher uplift rate to the north can be seen. For this particular ratio, you have increasing tectonic rate the higher the ratio gets. There's a trough here in the center where the transition occurs between the two mountain ranges. This is near Westgard Pass. And then you have this variation to the south. So, and this also is where the fault regime switches from normal to almost solely strike slip along the western INYO fault here. So this is somewhat expected. However, where the real usefulness lies is when you combine the many different indices into one figure, and then you can interpret what is happening here. And I'll show you that in a minute. So these are the questions I propose to discuss, and there are revisions to the White Mountains fault zone section boundaries appropriate. Those would be the ones defined by DePaulo and Bryant. Is there evidence of long-term Quaternary fault sections along the White Mountain fault zone? Can we reconcile the seeming geomorphic contradictions regarding uplift along the northern White Mountain Fault Zone? What is happening structurally at the White INYO boundary? How is tectonic activity along the central southern INYO section defined? And how significant is the influence of lithologic controls on fluvial geomorphology? So, excuse me 1 minute. The White Mountains Fault Zone sections. So, this is a graph of the combined geomorphic indices. You'll notice this should look familiar. This is the Basin Elongation ratio. The red arrow, just to remind us that an increasing ratio means that you have increasing tectonism associated with this particular ratio. And then this blue line here is the mountain front sinuosity. And this blue arrow is just to remind you that increasing tectonism is associated with a decreased ratio for mountain front sinuosity. And you'll notice that there are these dashed lines right here. And these dashed lines represent my revised section boundaries to DePaulo and Bryant section boundaries along the White Mountains Fault Zone. And the reason I decided that these were more appropriate is if you look at the mountain front sinuosity, there's a jump right here, right near Birch Creek. There's also, close to that, there's a decrease in basin elongation ratio, and then there's a change in some of the other indices as well, such as valley floor width to height ratio at this point. In the south, I moved the Hamel and Central boundary to this point near Sacramento Canyon, because once again, there's a sharp, significant change in basin elongation at this point, as well as a drop right after that in the mountain front sinuosity, and also significant changes in some of the other indices as well. Just for your reference, quickly, that's the DePaulo's original ones, and then obviously the black are my interpretation. So that was short term. This is more long term, persistence of Quaternary fault sections. This is the Piedmont range crest profile that I alluded to earlier. Here's the range crest, here's the Piedmont. This is the north, this would be north, the north section of the White Mountains. This is south, this would be the southern INYO Mountains here. And you can see highlighted here are the different segments. These are my revised boundaries, my proposed boundaries, not DePaulo's. And once again, when you see a sharp drop in Piedmont and range crest, it often can indicate that you have a salient block or a fault boundary at this point. This is exactly what we see here, and it corresponds very nicely with what would be Birch Creek. You see the drop in the profiles of the Piedmont and the drop in the profile of the range crest. Once again, at Sacramento Canyon, there's a sharp drop in range crest, and then at the central segments, I believe that those are appropriate boundaries. This shows that long term that probably is the case. You have a sharp drop here and a much smaller drop here in the Piedmont, but nonetheless at the end of the INYO section you have a sharp increase in the Piedmont and then a sharp increase in the range crest. One of the problems that were found along the Hamel section, one of the interesting things I should say, when just looking at the fault scarp morphology, which Apollo did, is that he noticed, and I noticed too, that you had this sharp increase, or decrease rather, in tectonic activity along here. And this is somewhat problematic because directly behind the Hamel section is White Mountain Peak, which is the highest peak in the range. So why would we have the highest peak in the range behind a area of relatively low tectonic activity, at least compared to what's directly surrounding it? Well, if we look down here at the blocks that and basins that Stevens et al. 2013 put together, you can see that something that is relatively close to these boundaries is also this North Bishop block here, which is that landslide slump where the basin actually becomes much more shallow. And you can see that this boundary with the central INYO and towards the top of the Montgomery section here corresponds with the White Mountain block, and then the White Mountain structural zone roughly corresponds with the INYO block, which also is suggestive of more long-term fault sections. This figure right here illustrates this even better. You can see the mountain front sinuosity here range foot strike here, valley floor width to height ratio here, and the basin fan area ratio here. And you can see once again, you have this change in range foot strike. You have this change, jump in mountain front sinuosity, and you can see the North Bishop block and how it corresponds with those different values. And then this is the fault dip values that Phillips and Michkowski measured back in 2011. And as I stated earlier, they were trying to see if they could find some sort of correlation between the angle of dip in the faults and what was going on geomorphologically, and they really could not. And I really could not either, and I don't think that this shows that there really is not much of a correlation between angle of dip and what's going on with the geomorphology. This is important. The basin area and alluvial fan size in particular is interesting because of the apparent contradiction in what's going on here and what's going on with most of the other indices. So increasing tectonic rate is indicated by a low basin area alluvial fan size ratio. This is, according to other indices, the most active area of the range, and yet we have the highest basin area and alluvial fan sizes here. This perplexed Phillips and Michkowski and perplexed me. So this is the problem of the fans. Why are these ratios so large, and why are there such large fans here? And so they, as I stated, said that, well, maybe this is because of fault dip. Well, that didn't seem to pan out. So back in 1993, Leader and Jackson wrote a paper, or did a study in the basin and range a little bit further to the east, where they looked at fault transition zones of normal faults. And they found that often in these zones where you have a zone of transition, you have these large alluvial fans opening or forming as basins open up. And what we have here is actually the Queen Valley Fault intersecting the Coyote Springs Fault and then the White Mountains Fault Zone. And there's almost a 90-degree bend right here in the northern White Mountains. And coincidentally, we see these large fans and these large fan basin area ratios. And I believe this is, at least so far, the best explanation. The White INYO boundary. What is controlling it structurally? Well, one of the prominent features at this area of the mountain range is the Wacoba lake beds. These jip gently to the west, and you can see the alluvial cap on top, and then the lake bed deposit jipping gently to the west. This is a little bit of a problem, though, because if they are part of the White Mountains Fault Zone, they should be dipping to the east, because this is the footwall side of the White Mountains Fault Zone, not this. So what's going on here? Well, there's a couple of different there's two primary things. One is the Deep Springs Fault, and I believe that it actually extends below the Wacoba INYO lake beds and into Owens Valley. And then a little bit off the map, you can't see it here, but it was illustrated earlier, is the Eastern INYO Fault Zone. And Lee et al. Did a study of the Eastern INYO Fault Zone and believed that this is actually uplifting at such a rate that it's tilting the beds this way. In other words, even though this is active, this has outpaced this, and that is a possible explanation. However, the Deep Springs Fault moving underneath here is also a possible explanation. And I'll explain that with my proposed development of the Deep Springs Valley and the Wacoba embayment. So roughly 3 million years ago, we have the Wacoba Lake. Well, the natural drain of the valley actually should be further south down to what Owens Lake is, where Owens Lake Drybay currently is. So why is there a lake here? Well, if there was a Deep Springs Valley Fault pushing up at this point, it could form a basin for water to pool. And then this time there would actually be no Deep Springs Valley and no Deep Springs Valley Ridge, because the fault would not have extended up into this part of the mountain range. The fault zone was not active. 2 million years ago, the White Mountains Fault Zone becomes active again. The Fish Lake Valley Fault Zone activates, and the Deep Springs Valley Fault begins to extend as it becomes a zone of accommodation between the Fish Lake Valley Fault Zone and the Owens Valley Fault Zone. And then we have uplift of the Wacoba lake beds begins. In the middle of these two time periods is when the volcanic eruptions start to begin in Owens Valley and the western INYO, western White INYO range. And then we have the formation of the Big Pines volcanic system, which happens to be right here, where if this fault does extend into, would be an extension of that, or it would be a pipeline as was put by other workers. And this also means that we would have the Deep Springs Ridge Formation here, and then the Deep Springs Valley opening up, and then eventually this becomes less active and is covered up by the alluvial fill on top. So the central southern INYO section. This is an important section because it shows, or at least illustrates, some of what's happening with lithologic controls versus tectonic controls. So this is a satellite image of Mazorca Canyon. That's boxed in red here, and this is the main canyon right here. And the orientation is structurally controlled and parallels the bedding. And you can see these different beds. And it's one of the only large stream, in fact I think it's the only large stream in the entire White INYO range that trends north-south. Which was, if it was being controlled by tectonics, would seem to make more sense that it would be draining out east-west like all the other drainages are. And to the north of this, you can see the White INYO fault zone extends this way, the Owens Valley fault zone extends this way. They intersect right off the image, and this is also where the Wacoba INYO boundary is as well. I'll also say to the east of this is where the Eastern INYO fault zone begins to become more active, and this it becomes the normal area of normal activity, and this is now an area of strike slip activity. So finally, the influence of lithology and geomorphic indices. I did a number of stream profiles, and here's two: Montgomery Creek and North Mazorca Peak Canyon. This is one of the very most northern drainages. It also happens to have one of the lowest K values, which would imply a low tectonic activity, even though it is in a high tectonic activity area. This upper half of the stream is predominantly made of granite. This lower half is made up of metamorphosed carbonates. And as you can see, if lithology was a primary control at this section of the mountain range, we would expect to see some sort of bump or change in the stream profile, and yet we see nothing. So it would appear that tectonic activity actually is much more of a strong control than lithology on this particular stream. Now let's contrast that with North Mazorca Peak Canyon, which is an area associated with low tectonic activity. This is much further to the south. This is near the Wacoba INYO boundary, and we have Cambrian marine rocks making up the 70% upper portion of the stream channel, and then we have a set of Quaternary volcanics making up the lower 20 to 30%. You can see this is convex, or convex upwards along this portion, and then we have a nick point right here, and then shortly after we see a begin to change in gradient where it becomes slightly concave up at this point, right near the point where the Quaternary volcanics are. This could indicate that this is much more resistant long term than this is. This is also, as I said, along the West INYO fault, where tectonic activity shifts over to the Eastern INYO fault, and this could be indication as well that this is being pushed up, as Leith suggested, because it's closer to the Eastern INYO fault zone at a much faster rate than this is over here. So in conclusion, Google Earth is an effective method of measuring geomorphic indices based on its ability to reproduce prior geomorphic studies. Geomorphic analysis of the White INYO Mountains shows tectonic activity increases northward. Sections of the White Mountain Fault Zone should be redefined, or I'm suggesting they be redefined by long-term Quaternary tectonics rather than by short-term fault scarp morphology. The Deep Springs Fault likely extends into eastern Owens Valley below the Wacoba embayment, providing a strong structural boundary between the White INYO Mountains. And when tectonic activity decreases, lithology exerts a stronger control on fluvial development. So, quickly before I end, I'd like to say thank you to Dr. Jeffrey Knott for helping me out. I live up in San Luis Obispo County, and he did a lot of the administrative work, which means taking papers to the office for me that I probably should have done or should do if I lived here. So he among other things that he did, he really helped me finish this degree up, I think more so than many advisors. No offense to the rest of the instructors in the room. I'd like to thank my committee members too, Dr. Phil Armstrong and and Natalie as well for agreeing to be on my panel. And then the White Mountain Research Center provided me a nice grant so I could go up there and do some run around in the White Mountains and check some of my observations in the field. The Jonathan Davis Award, which was also granted to me for a previous thesis I was going to do, which ended up turning into this. My wife is not here, but I want to be on the record to the camera that I'm thanking her because she really pushed me to do this. I wouldn't have finished it without her. And then, of course, Google. They provide Google Earth. It's free, so I got to give props to them. So thank you, Google. And with that, I'm done. And if there are any questions, I would be more than happy to take them.